Assalamualaikum everyone. This is our project titled Computer Vision Based Vegetable Weighing and Billing System developed for the 4518 Electrical and Electronic Systems Laboratory. The idea behind this project is to create a smart vegetable weighing system that can automatically recognize the vegetable, measure its weight, and calculate the bill without requiring manual identification or price entry. The project was developed by our team Azonens, combining computer vision, embedded hardware, and software integration into a single working system. Let's look at the workflow of the system. First, the customer places vegetable on the weighing platform. Then the camera captures the image of the vegetable, and our trained YOLO-based model detects which vegetable it is. At the same time, a load cell sensor measures the weight. The system then calculates the price automatically based on weight and unit price, adds it to the cart, and finally generates a receipt after the transaction is completed and also stores the transaction record in the database. This creates a fully automated vegetable billing system. On the right, you can see the final prototype of our device. First step in developing the system was preparing the dataset used to train the detection model. For this, we used the RoboFlow platform, which helped us organize and annotate the dataset. Here you can see part of the dataset interface. The images contain vegetables commonly found in local markets. Many of these images contains both single item and multiple item samples, which allows the model to learn how to detect several items of a particular vegetable at once. Each vegetable instance was manually annotated by our team using bounding boxes, assigning a label to every object in the image. After annotation, the dataset was organized and prepared for training. In total, the dataset contains about 4,900 images, which were divided into training, validation, and test sets. The images were also resized to a consistent resolution, and several simple augmentations such as flipping, brightness variation, and small rotations were applied. These steps help the model perform more reliably when it encounters different lighting conditions or camera angles. The model was trained using YOLO V8 on Google Colab, which provides free GPU access, making it suitable for deep learning experiments. During training, the model learns to detect different vegetable classes by reducing loss values and improving prediction accuracies across multiple epochs. The training graphs show how the model improves during training. On the left, you can see the training and validation losses decreasing, which means the model is learning effectively. On the right, the precision recall and MAP scores gradually increase and stabilize, showing that the detection performance becomes consistent as training progresses. After successfully training and validating the model on Google Colab, the best performing weights file was loaded in PyCharm, where we implemented real-time detection and serial communication with Arduino. The YOLO V8 model runs in PyCharm using the Alternatives framework. At the same time, the Arduino continuously streams weight data through serial communication. Using the PySerial library, the Python program reads the incoming weight data in a non-blocking manner. This ensures that detection and weight acquisition operate within the same real-time loop without causing delay. The detected vegetable class from the YOLO model and the measured weight from the load cell are then synchronized within the program. These two parameters are passed to the billing logic. This is the code that was used to test and implement the integration of detection model and Arduino serial communication.
Till now, you have seen how the dataset was made and how the model was trained using YOLO version 8. Now, I will be showing the codes for overall working of the project. Several Python modules were written in order to make the project functional. The camera UI is the main file and the head of all the codes. This file uses a pytorch.pt, a pytorch file based.pt, which was generated from the training of the model. Besides this, there are many other supporting modules which are called within the camera UI.py to handle different tasks. As for example, the weightreader.py. This was used for reading weight from the Arduino load cell through serial communication. Database.py for storing all customer and transaction data in an SQLite database. Receipt.py for generating PDF receipts automatically. Export.py for exporting sales data to CSV and Excel files. All of these codes are uploaded in the GitHub repository. The link is given in the description below. I will now be showing the working of the project. First of all, I have to run this file. Before that, I have to make sure the virtual environment VNV is activated. Because inside this VNV, all the modules and dependencies like PyTorch, Ultralytics, OpenCV, and PySerial were installed within this VNV. After running this file, it will take a few seconds to load the YOLO and initialize the camera. So let's wait for a moment. So as you can see, a window has popped up. This window asks for the information of the customer, their name and the mobile number. So let's put the information in. and the mobile number. Okay, then we'll click on start billing. Then the main interface of our whole project appears here. On the left side, there is the live camera feed showing that what the camera sees in real time. On the right top corner, the customer's name and the mobile number are displayed in order to ensure the correct customer is being served. Below that, there is a section labeled live transaction where the detected vegetable name, its weight, unit price, and the total calculated price are updated in real time as the items are scanned. The description of the other section will be given along with the demonstration. Now I will be showing how our project actually works, the live demonstration. So at the left part of the screen, you can see the live view of the camera. The load cell is empty now, the scale is empty now. So let's at first put a potato on the scale. And as you can see that it has detected the potato. If we put another potato, the weight will be updated. It is the detected item, the weight will be updated and the unit price will also be updated. Once the weight and the price both are stable, if we remove the potato from the scale without pressing any kind of button, the weight and the price of the potato will be updated here in the cart. You will see that now. So here the weight, the total price have been updated. Now we'll do the same thing sequentially with tomato, with cucumber, with chili, and at last with onion. Let's see. There is another feature. If a customer, for example, doesn't want potato, he can select the potato. He can click on delete selected item and the potato will be removed and the grand total will be updated as well. There is also a provision of updating the prices of the vegetables according to the current market rate. Now, once we click on finish session, a confirmation window will pop up showing the summary confirming that the data has been saved to the database, the Excel sheet has been updated, and a PDF receipt has been generated. The PDF will be like this one. This is the PDF of this is the PDF format of the receipt of the customer who has just bought the items. Here you can see the grand total, the weight, the item the customer has bought, all have been shown here. And all the transaction data is stored in the Excel sheet as a cumulative sales log. So here we can see all the data. This is the last data of the customer. And here all the data are also saved here. And once everything is done, the program resets and it is ready for the next customer to appear. Now we have made this entire application portable. Till now I have been running this using VS Code through the Python script, but in real life scenarios at market, super shops, their computers don't have Python or VS Code or any other code editors installed. So we used PyInstaller to package the entire application into including Python itself, all the libraries and the YOLO model into a standalone .exe file. This means we can simply copy the exe folder to any PC using a pen drive, plug in our Arduino device to the laptop's USB port and run the application exactly the same way without writing or installing anything. So as you can see, this was my laptop. This is the laptop of a friend of mine and this is the pen drive. In this pen drive, I have the .exe file now. I will plug in this pen drive into my friend's laptop, copy the .exe file in this laptop. So this is the screen of my friend's laptop and there is the folder where there is the .exe file. Now I'll be copying this file into a folder of my friend's laptop. As you can see, the file is going to be copied. So we have to wait for some time for the file to be copied. Let's wait until the file is being copied fully. So as you can see, I have copied the folder. Inside the folder, this is the .exe file, and if I run the exe file, the same window is supposed to come with an additional feature of settings. It will take some time to load the camera, the YOLO model, and everything else. So let's wait for a moment. As you can see, in the portable version, we have also added a settings screen so that the user can select the correct COM port, the baud rate, the camera ID, and the YOLO model file according to the system. So here we select the COM 10, the baud rate is fixed, the camera ID is 1, and we can also select the PyTorch file. So here we'll be selected it now. And now if we click on save and continue, it will take us to the screen where we will have to give the input of the customer and their phone numbers. So let's wait. So as we can see, we have got the same interface where we'll be putting the customer name, the mobile number, and if we click on start billing, oh, sorry, If we click on start billing, and we will see the exactly same interface as before. Put like tomato on the scale, it will detect the tomato, it will measure the weight and give the prices, as you can see here in the screen. If I remove the tomato, it will be updated as previous. Click on finish session, a window will pop up. The PDF, the Excel sheet, all will be saved in the same folder as it is in the exe file. The sales data are saved right in the same folder where the exe file is located. So here in the sales data, the sales log.xlx file, here you can see the information of the customer who has just bought the potato. All the codes are uploaded here in the GitHub repo. The codes for the portable bill, then the codes for the software part is also here. And besides all this, there is a detailed README file that instructs how to run this software in any of the laptops. Besides this, you can also find the portable software here in the releases as well. This is, in short, the overall software demonstration of the project. Now, Samyak Karmit will be explaining the hardware implementation. Thank you.
For the hardware implementation of our project, we used an Arduino Uno paired with an HX711 module and a load cell to measure the weight of the vegetables. To obtain visual feedback, we used an A4 take camera. We selected these components mainly because they are easily available and have a larger user community, which makes development and troubleshooting much easier. The exterior structure of our setup was designed entirely using Tinkercad. The base of the system is 3D printed and includes screw holes to securely mount the load cell. We also designed 3D printed support bars to elevate the camera, along with a camera case to hold it firmly in place. In addition, we created a plate-like platform where the vegetables are placed directly under the camera, ensuring clear and uninterrupted visual input. For the circuitry, the modules are connected as shown in the diagram. To reduce wire complexity, we soldered headed pins and the HX711 onto a variable which can be easily mounted on top of the Arduino. Since the calibration factor of the load cell can vary, we tested several known weights before determining the correct calibration value. As demonstrated, all the components used in this system are readily available and user-friendly, making the setup easy to assemble. Overall, our design functions as a plug-and-play system that anyone can build and use with minimal effort.
Allô Lélo